In a previous video, we were introduced to parametric equations. We learned how to set up your normal y and x as functions of some sort of third variable or parameter, which often we use as like t or something like that, because usually there's some sort of independent parameter like time that's keeping track. However, it's pretty common that you will have two functions that are both functions of time, but they also interrelate. And we want to see how those two things relate to each other with derivatives, but the problem is that it makes the most sense to talk about it in terms of time. So give me a second and I'll explain. For instance, we have this x and y here. So this is a trajectory. This is the case that we talked about in a previous video, the person throwing the ball at some sort of ground level origin at a 45-degree angle. And we said that the x position is determined by this function, and then we said that the y position is determined by this function as a function of time. So what you might want to do is you might want to figure out what the derivative is. How is this curve changing, or how is the slope of this curve changing? But the thing is that it actually makes sense to determine that slope as a function of time. What I might want to know is, okay, how is this curve changing at time equals 2 or at time equals 5? Right? That's important to me. So it's not as important about how y is changing when x is changing. What's important to me is how the slope is changing at a particular time. Hopefully that makes sense. If it doesn't, rewind and see if you can't understand it. But the idea is that we don't want our normal dy dx as a function of x. We want it as a function of t. We say, okay, I want to know what the derivative is, or what the slope of the tangent line is at this time. So that's kind of an interesting new play on what we've done before. Well, there's a really cool idea here, and I won't go into the mechanics of proof of it, even though the proof is kind of neat. And it's the idea that if I have two functions which I have two variables which are both functions of a third parameter, t, so this is a function of t and this is also a function of t, then the derivative of y with respect to x can actually be computed by taking the derivative of y with respect to t divided by the derivative of x with respect to t. Now this looks a whole lot like you're going to be treating them as fractions and canceling. Disappointingly, that is how it kind of feels. But what goes underneath is a little more complicated math. Now, the key here is that derivative of x with respect to time can't be 0, or you're going to have, that thing's going to explode on the bottom. But ultimately, if you take the y derivative in time divided by the x derivative in time, again, treat it like a fraction, it's not, you get this dy dx. So let's do this on the example that we have here. I say, okay, well, I've got this parametrically determined curve. What's its derivative with respect what's dy dx in terms of that t parameter? So I say, all right, if I take the derivative with respect to x of this, well, the t just drops off. I'm sorry, the derivative with respect to t here, the t just drops off. And then the derivative of y with respect to t, power rule brings down the power, so you have negative 32t, and then the t disappears here as well. So you have negative 32t plus 24 square root of 2. Then to get dy dx, you take dy dt and you divide by dx dt. So dy dt divided by dx dt. And then when you take this here, that square root of 2 should be on the bottom. So instead of writing it on the bottom, I'm going to write 2 root 2 over 3. My apologies there. That's 2 root 2 over 3 t. And then those two are the same, so that becomes plus 1. So that gets us what we might have expected in terms of our derivative. What's neat about this is that going over here, I can get the value of this slope, not based upon what x is, but based upon what time is. So you can know, oh, that thing's shooting up really quickly, or it's not, based upon the t parameter, not based upon the x value. Really useful stuff in like real world applications, and this extends really well to when we start talking about the idea of vectors and things that have multiple dimensions, and so the parameter is actually driving the how this thing is moving through space. Really good stuff. Now, with higher order derivatives, we have to be a little more careful. So if I have the second derivative, d2y dx squared, if you looked at this thing like a fraction, you would say, oh, well, I'll just take the first derivative squared divided by the second derivative squared. That's not true. That is not how this works. And so this is a good example of how these things are in fact not fractions. What you have to think about instead is this idea of a y prime. So the second derivative is really the first derivative of the first derivative. Does that make sense? Second derivative is applying the derivative operator to a derivative. So that's how you get your second derivative. And the reason I say it like that is because if this is not dy dx, it's just some function, right? If it's y prime or whatever, then this is like dy prime dt divided by dx dt. So let me kind of write that. If this were y prime, if we were saying something like that, that's not really good notation, but just bear with me here. If I have this like this, then I can follow this format. And I can do that fractional form, as long as I'm saying I'm taking the derivative with respect to t. So what I want to do is I want to find the second derivative, you have to find that first derivative, just like we did here, and then take its derivative with respect to t. Now what's neat is you actually already have dx dt, because to compute this, you had to already compute dx dt. So that's a one-time compute. You just have to compute one more derivative and then divide. So if you want to take the third derivative, you do the same thing. You've already computed this, so you need to take its time derivative and then again divide by dx dt, which you've already done. So when you're taking these second, third, fourth order derivatives, hold on to this, and then you're just going to keep applying the time derivative operator here and dividing, and that's going to get you what you want. So we're going to apply a few of these, try to shore up those skills, but in fact this stuff's actually a lot easier. If this was confusing, I apologize. I promise once we get to doing it, it's going to become really easy.